Our next type of reaction will be single replacement reactions. These are known as substitutions as well. An example of this would be the following. These generally form the pattern, of some element plus some compound turning into a different compound and kicking out an element. So you end up with an element and a compound on your left, on your reactants, and an element and a compound on your product side. What these reactions look like is, notice we have a metal here that has become a cation, or rather we can say an element, we'll say that way. Yeah, it'll be easier. We have the hydrogen, which is a cation, in this particular reaction, turning into an element. So notice that because zinc and hydrogen both form cations, that's what's being replaced. We're not kicking out the chlorine and making a combination of zinc and hydrogen. That would be very unlikely. Chlorine is a much better anion than hydrogen is. However, we can see that we can replace anions as well. So say if we have Cl2 plus NaBr, for example, we can indeed get Br2 plus NaCl. So we can kick out anions. What you want to do is evaluate, is your anion, or is your element that's coming into the reaction, is it more likely to form a cation or an anion? So Cl2 generally prefers an anion. It prefers to be an anion, right? So we're going to kick out the anion of our compound in our reactant. So this kicks out the anion and replaces it. So this is why we call it single replacement. One thing is being replaced. In the first case, we're kicking out hydrogen and replacing it with zinc. In the second case, we are kicking out bromine and replacing it with chlorine. Remember for all of these that we have to also remember to charge balance. That's why zinc chloride is ZnCl2. We also need to remember our diatomic elements. Hydrogen, chlorine, and bromine are all diatomic, so we need to indicate when they're in their element form that they have the 2 there. All right, very important. We can tell, by the way, if we look at the net ionic equation for that first reaction, go ahead, pause the video and do it. All right, you should see for the net ionic equation, if you've balanced it, gives you the following. You have solid zinc. By the way, metals, of course, are generally solid at room temperature. Zinc is a metal. We have our aqueous acid. We formed an aqueous ion, and we formed a gas. Hydrogen is a gas, right? So don't forget to check your periodic table for elements. Most metals are solids. Hydrogen is a gas at room temperature. And of course, our zinc chloride should be soluble because chlorine tends to make things soluble. Chlorine forms a gas at room temperature. Sodium bromide should be aqueous. The bromine is actually liquid. That's a one-time thing. Bromine and mercury are our only liquid elements. You know what? Have we talked about that on the periodic table? Maybe. Let's see. Your periodic table should have an indication of solids and liquids and gases here. Let's see if mine does. Mine actually doesn't, believe it or not. But I have a different periodic table somewhere here. I'm just lying to y'all, aren't I? No, we've got one. All right, I don't know where it is. Okay, I lied. That's okay. Your periodic table, if you find one, should have mercury and bromine as liquid, hydrogen, oxygen, nitrogen, chlorine, and all the noble gases as gases. So I'll just write this out because apparently my periodic table doesn't show that. And we'll take a look at that ionic equation bit right after this. So note, liquid would be Br2 and mercury. gas will be hydrogen, oxygen, nitrogen, fluorine, chlorine, and noble gases. Everything else is solid on the periodic table at room temperature, so we're going to indicate its state of matter otherwise. All right, so anyways, now that we have that state of matter business dealt with, we've got the zinc and the hydrogen switching places, and our net ionic equation was the following. Notice here, in this case, we actually have a change in the charge of these components. Our zinc used to be neutral, or we could say its charge was 0. And over here, it's got a +2 charge. And we've got hydrogen going from a +1 charge to no charge. No charge there. Remember that the only way for ions to form, or charges to form, is by transferring electrons. So we're going to see all single replacement reactions will fall under the category of reactions called redox reactions, which are electron transfer reactions. Reactions that involve charge changes, and more broadly, we'll talk about them in the context of molecular compounds too. We call these reduction oxidation reactions, or redox reactions. So reduction, oxidation, redox reactions. These involve electrons change. So we can see here that the zinc is losing 2 electrons over the course of this reaction, and the hydrogen is gaining those electrons because it's going from positive to 0, right? It's becoming more negative. The zinc is going from 0 to positive, meaning it's lost electrons. We have terms for these. When a substance loses electrons, or becomes more positive, we call this oxidation. And when something gains electrons, meaning it becomes more negative, that's the reduction part. So it becomes more negative. It doesn't have to become negative, it just becomes more negative. Like hydrogen went from +1 to 0 in this reaction. So that's more negative, right? It's not actually making a negative number in this case, but it's becoming more negative. And the same thing here, it really becomes more positive. So it doesn't have to be negative or 0 to start with, it just becomes more positive. All right, and this second process is called reduction. So in our reaction here, I'm going to copy it below. Nope, that's a secret. That's from another class. Let's hide that. Okay, evidence destroyed. Let's go ahead and copy our equation again here. See that? Oop. There, we've got our equation. We see here that the zinc is becoming more positive, and therefore in this reaction, zinc is oxidized. And hydrogen is going from +1 to 0, and so we can see that in this reaction, hydrogen is reduced. So we just talk about the element when we're saying what's oxidized, what's reduced. By the way, importantly, reduction and oxidation always occur together. You cannot get only one of these happening. You can have multiple reductions happening as long as you have at least one oxidation. You could have 3 reductions and 3 oxidations happening at once. That's fine, as long as you have at least one of each. You can't have reduction without oxidation. You can't just lose electrons into nowhere. Something has to take those electrons. So we have to have both processes happening at once. In the next video, we're going to learn a way of accounting for the electrons in the course of a reaction. While it may be more obvious with these ionic ones, using ionic compounds, with molecular compounds we can apply redox rules as well.